Hello, I am Pankaj Sharma from Brainleague Learning. Today, we will build an intuitive understanding of Kirchhoff's laws, the sign conventions, and solve two example problems, one for current at a node and one for a voltage loop. First, Kirchhoff's current law, often called KCL, at any node or junction. The sum of currents flowing into the node equals the sum of currents flowing out of the node. Because charge cannot pile up in a node, what goes in must come out. Sign convention for KCL. Choose a direction for each current at the node. We will call currents entering the node positive and currents leaving negative. Then, the algebraic sum of all currents at the node equals 0. Let's draw a node and three currents to visualize KCL, and then solve a simple example. We will assume I1 enters from the left, I2 leaves upward, and I3 enters from the right. Worked example for KCL at node A. Suppose I1 equals 4 amperes entering, I2 equals 2 amperes leaving, and I3 is unknown but assumed entering. Our sign choice is entering positive and leaving negative. So we write I1 plus I3 minus I2 equals 0. Substitute values. 4 plus I3 minus 2 equals 0. So I3 plus 2 equals 0, which gives I3 equals negative 2 amperes. The negative sign means our assumed direction for I3 was opposite to reality, so the actual I3 is 2 amperes leaving the node. Now, Kirchhoff's voltage law, or KVL, in any closed loop, the sum of voltage gains equals the sum of voltage drops. Equivalently, if you walk around the loop and add sign voltages, the total is 0. This is conservation of energy in circuit form. What the sources give, the elements like resistors take. Sign convention for KVL, pick a loop direction, clockwise or counterclockwise. When you cross a source from negative to positive terminal, record a voltage gain, positive V. From positive to negative, record a drop, negative V, across a resistor. If your loop direction matches the assumed current direction, it's a drop minus IR. If opposite, it's a gain plus I. Here's the circuit we'll analyze. Two loops, loop 1 and loop 2. Resistances R1 equals 4 ohms, R2 equals 6 ohms, R3 equals 3 ohms. Two batteries, E1 equals 12 volts, E2 equals 6 volts. Currents I1 and I2 flow clockwise in their loops. Notice that R3 is common to both loops. That's where the two currents interact. Let's apply KVL to loop 1. Starting from the positive terminal of E1, we get 12 minus 4, I1 minus 3 times I1 minus I2 equals 0. Simplify it, 12 equals 7, I1 minus 3, I2. That's our first equation. Now, moving to loop 2 and going clockwise, minus 6 plus 6, I2 plus 3, open parenthesis, I2 minus I1 close parenthesis equals 0. Simplify it, negative 6 plus 9, I2 minus 3, I1 equals 0, or 3 I1 minus 9, I2 equals negative 6. That's our second equation. Now, solving the two equations, 12 equals 7I, 1 minus 3 I2, and 3I, 1 minus 9 I2 equals negative 6. After solving simultaneously, I1 equals 1.5 amps, I2 equals 1.0 amps. That means the first loop current is 1.5 amps, 1.5 amps, and the second loop current is 1A. At the junction where R3 connects both loops, the current through R3 equals I1 minus I2 equals 0.5 amps. Current entering the node equals current leaving, so KCL is verified. So we used Kirchhoff's laws to apply KVL in each loop, form simultaneous equations, and verify KCL at the junction. That's how you analyze any DC circuit systematically. If you found this helpful, don't forget to like, subscribe, and share this video. Up next, we'll solve Wheatstone bridge problems using Kirchhoff's laws. See you in the next session on Brainleague Learning.